Right. Now out of this 45 participants, there are 17. The number has gone down for some reason. There are 17 persons who are working and studying, right? So for them, especially for them, my advice is to plan your study time, right? Now, all what I can see is that you are struggling at the end and you are trying to cram things. You try to do copy classes, you try to get leave out of your job and panic yourself, start studying in groups. It's not going to help that much, especially in my subjects. I am teaching you 3 subjects. I don't know how many of you are following 3 subjects of mine. I am teaching this subject, then I'm teaching 4241. I'll be academically coordinating. In fact, I'm not teaching. We are not supposed to become teachers to you according to this open and distance learning mode. But anyhow, I'm trying my best to give you out of limited time we have. So I'm doing 3 subjects, 4241, which is high engineering hydrology. Then I am doing this subject 6345, and I'll be also doing 5440, right? So please note that it is quite difficult to pass if you just cram it at the end. So I'm just trying to make you aware of basically you have to dedicate few hours for your studies and you have to plan out your studies. I don't know how many of you have taken how many subjects. For example, if you're doing 5 credits, it means 500 hours. And it's fairly high amount of work that you have to do. And please dedicate yourself. Let's say if you are having 2 hours to work, I always recommend you to take adequate amount of work that you can cover out of these 2 hours. And you have to continuously engage with your studies. Then I would like to go into the synopsis of this course. And don't worry, I'll be taking several extra lectures to this course. Please attend to all of these extra lectures. I'll be conducting extra lectures mostly after 7 o'clock, because we have working students. So what do you say? If I do extra classes after 7, will it be okay for you? Can somebody answer?
Okay, sir.
It's fine, right? I mean, after 7, you are quite free, right? After coming from work and so basically, I am supposed to have four day schools for you for this subject, but 4 day schools are certainly not enough. And I'll be conducting a little bit more classes. I know a few more classes other than these 4 day schools. And I'll just go into the synopsis. 1 minute, please. Right? I want to brief you few things on this course. Can you see the screen? Can you see the screen? Okay, now this is the course synopsis of your subject, right? I don't know how many of you have seen this. Now, under this, there are several things that you need to do, right? Now, the one thing is to have CAT exams. You can see here, CAT exams. Then you have lab classes, right? Nearly, I think about 10 experiments we will do to you to get an understanding about the subject. Then everybody will have to do a mini project. So you will have to select a topic, environmental engineering topic, and you will have to perform a mini project and you will have to submit a report. Then there is a field visit. Last time I had to do it virtually. I had to make a video and do it virtually because of COVID. But this time, due to practical issues like fuel issues, things like that, again, we may have to do it virtually. But I prefer to do it physically because it could benefit many of you. So after doing this field visit, you will have to submit a field visit report. Now you can see in your eligibility criteria, you have marks for tutor mark assignments, you have marks for CAT, you have marks for lab, then you will have marks for mini project, and you will have marks for field visits. So you can see here, it will be count only if you have above 40% for field visit and mini project, right? So it is compulsory. And also the lab classes are compulsory for you. CAT are compulsory for you. So it's not a job, right? So you have fair amount of work, you have fair amount of individual work, and you have to submit. Now, regarding mini project, I will be giving you few topics. You can select one topic out of that, and you will have to inform me the topic that you have selected, and I'll give you a deadline to submit. I think the deadline is already there in the activity diary. I have put it this time. You can see it. Then also there is a deadline for field visit report. Then there are deadlines for laboratory works. You have to submit on deadline. This is quite serious. Why I'm saying is that you are supposed to become engineers, so you have fair amount of working people here. So you know the significance of submitting things on time, right? Now, if you are submitting bids, if you are completing projects, it's quite important to achieve deadlines. So for the freshers who are doing here, who have no work experience, this will be a good exercise. So I don't need any excuses. I have that and this because we are going to announce these deadlines far ahead, right? You will have plenty of time. Do not wait until last moment to submit things, because your deadlines will be deadlines, right? We won't have time to entertain. We are on a very rush program, and please be professionals and try to submit things on time, right? So I'll get into the subject. Can you see the screen? Can you see the screen?
Yes, sir.
Yes, sir.
Oh, okay, good. Now, now your block 1 contains ecological aspect of the subject. I will do it later. Definitely, I'll do it within coming 1.5 months. But I thought of starting it from session 4, water treatment, because it's a very significant and a lengthy session, and especially for you to get the feeling of the subject, I thought of starting the lesson from this session. Sorry, the course from this session. Apparently, I would like to know how many of you are from water board or any water resources board or irrigation department. Could you please raise your hands? Again, I can see. So I think a few are there, right? So I can see few people are there. So this will be very important for you. So what I will cover under 6345 are the basics, but the real designs of the subject will be taught you under 7242. I don't know how many of you have registered for 7242. It is also a compulsory course. We had a course called 6533 in the interim curriculum. Now we are doing this course in revised curriculum. Now under revised curriculum, we have 2 courses. One is cvx6345. The other one is cvx7242. Now you will have to complete both the courses in order to be eligible to obtain your degree. Now let's move into the subject. Now, basically in this subject, we will be mainly talking about water, and besides water, we will be talking about air and noise as well. Now, water is a very interesting substance. Without water, we will not survive in this world. Now, water contains very unique properties. Now, because of this uniqueness of water, the life on Earth was evolved. That is what scientists says. And because of these unusual properties, it also has a very high tendency to become polluted. Now, if you look at the temperature of fusion and vaporization of water, it has a fair high range. Now, water fuses at 0 degrees centigrade and vaporize at 100 degrees centigrade. Now, this temperature range from 0 to 100 is quite significant for life to flourish. And without this temperature range, scientists says that the living things on Earth would have never begun. So we will further move into that. Now let's talk about the volume of water available on planet. Now, if you take our blue planet, our Mother Earth, 71% of the surface of Earth is covered by water. And out of this coverage, we have freshwater resources, something like 1,387 into 10 to the power 6 cubic kilometers. So that's the volume of fresh water available on the planet, which can be used by living things, especially humans. Now let's talk about the distribution of water. You can see the rivers as 0.0001%, and atmospheric humidity contains 0.001%. Lakes contain 0.016. Then the groundwater 0.61. The glaciers and polar caps has 2.24%. Then the oceans contain very high amount, 97.1. Now, out of all of this water, we can use fair extent of river water available. We can use lake water. We can use some amount of groundwater, not all. Then glaciers and polar caps, we are unable to use that much. Then of course, ocean water. Nowadays, we are having treatment systems to use it, but they are fairly expensive. So you can see out of the total available water, there is very small quantity of water available for human consumption. So it's not a joke. If we run out of water, we cannot survive. In fact, in coming few decades, there will be war on water. And you can see in the internet and you can see the predictions by scientists. So it is fairly important to preserve water and to keep it clean. Now, I will briefly talk about the hydrological cycle or the water cycle. Hope you have studied this from grade 6 onwards. In fact, we are studying about the cycle in detail at cvx6345. Can somebody raise your hand if you are doing both the 6345 and 4241? Are there any students who are doing both these subjects? No? Okay, good. Now, okay, 6 participants raise hand. So we actually, what we are studying under engineering hydrology is about this hydrological cycle or the water cycle. So we will be talking about that tomorrow. I'll be having a day school tomorrow for hydrology. Now, if I talk about this hydrological cycle briefly, now the cloud formations are there. Now clouds get densified and provide rainfall. And this rainfall will be captured by the surface. Part will run on the surface, part will go beneath and will flow laterally to the earth's surface. We call them subsurface flow or interflow. Then part will reach the groundwater table. We will be talking about groundwater table and the type of aquifers and various things under that subject. Now, then everything will flow into ocean. Meanwhile, flowing, part of it will be trapped by the plants, which will be transpirated to the atmosphere. So the plants will have a transpiration through its leaves. Part of it will be evaporated from the surface of the earth, and part of it will be in the clouds. So likewise, this water cycle will be taking place on earth. So basically, with this water cycle, if we pollute at one location, there is a high tendency for that pollutant to get dissolved in water and travel along the water cycle or the hydrological cycle. So this will result in contaminating an entire planet. which is happening right now. Now, this is what I just discussed before. The pollutants can travel with the water cycle. You can see if you dispose contaminants to the ground, it can percolate or infiltrate into the water tables, and it can contaminate the rivers, and it can evaporate and contaminate the clouds. If you pollute the air, the polluted air can be trapped in the clouds, and pollutants can come down with the rain, can harm your farm fields, can harm your health, can harm your food supplies. So they are all interconnected, right? Now, let us briefly talk about the sources of water pollutants. Now, if you look at the sources of water pollutants, you can basically categorize into two categories: natural and anthropic origins. So, natural, of course, you know what natural means. Anthropic means human-based or human-produced origins or human-created causes. So, when it comes to natural sources, especially gases from atmosphere, and then liquefaction of salt in soil, this is accumulation of these ions, cations and anions on soil. Then organics from living organisms, decompositions, things like that will produce pollutants. Then when rainwater erodes surfaces, it can create suspended solids in particles, and microorganisms, harmful microorganisms could be captured in these particles. Then when it comes to anthropogenic reasons, so we do these basic activities with water, industrial productions. Then we do discharges from municipal and domestic wastewater. Then we have discharges from farming and fishing. And you can see the contribution from each sector to the pollution. In fact, industrial production contributes 20% of water pollution. Then the municipal and domestic wastewater produce 10% of water pollution. Then basically the majority of water pollution, the major cause of water pollution is by farming and fishing activities. Now, especially in industrial production, the formation and extraction of raw materials, then the intermediate production, the heat transfers to cooling and cooling towers, you know what is happening at Noracholi, things like that can be considered as pollutions for water. Then discharges from municipal and domestic wastewater, the food, fecal and cleaning waste. Fecal means, you know, our night soil contaminants can create water pollutants. Then from farming and fishing, especially pesticides, herbicides and industrial waste, farming waste create pollutants to water cycle. Now, then there are, if you look at the type of sources based on the geographical origin, we can divide them into two categories. The one is called point sources. The other one is called non-point sources. Now, point sources, for example, localized industrial discharges. You might have a factory which uses water and produce wastewater. It might be discharging that wastewater from one location, at one location. So it is at a point. So the pollutants coming into the environment at a point. So that sort of sources are called point sources. Now, when you go into non-point sources, especially fertilizers and herbicides, especially in agrochemicals, they are non-point sources. When you apply them to at the environment, the pollution can take place at several locations. So you cannot finger point one point. So that's why we call them non-point sources. In fact, dealing with non-point sources are much more difficult than dealing with point sources. Then, when it comes to the water flows, which contains pollutants, we can classify into these 4 categories: white or rainwater, domestic wastewater, industrial wastewater, black or urban water. Now, rainwater can carry atmospheric pollution, human activity waste, traffic waste, vegetable waste, leaks. So basically, you know, when vehicles run on roads, they produce pollutants, and all these pollutants are exhausted, and part of it will be on the road. So when rain hits the road, so it can create this traffic waste, what you call traffic waste. Then again, if you look at certain streams in our country, especially adjacent to villages and cities, people used to throw waste into these waste streams. So when rain comes, it can create flood runoff, and with the flood runoff, it can carry all the waste into the undesirable locations. Then atmospheric pollution. Yes. Now, when we exhaust pollutants to the atmosphere, it could get dissolved in rainwater and come down, especially acid rains. Now, how many of you are from Kandy? How many of you are from Kandy? No one? No one from Kandy? Well, those who live in Kandy might have experienced acid rains, right? Now, according to Professor Ilaperuma at Teradini University, we get around 100 to 200 acid rains every year now. Because Kandy, especially Kandy city area, has severe air pollution. And because of this air pollution, we have to, this air is polluted, and the pollutants get into the rainwater and it comes down in the form of water. Now, when it comes to domestic wastewater, this is what we will be dealing mostly in this subject. The discharges to municipal sanitary systems, especially from households, commercials, and in large facilities. Then industries, you know, the toilet wastewater and the wash water can be considered under this. Then when it comes to industrial wastewater, you know, of course, if you have tanning or industries which use water, so the wastewater will be disposed to the environment. Then when it comes to black and urban water, now this black water is specially used for water that is contaminated with fecal matter or urine. So those are called black water. Now, let me summarize the water pollution that we were talking about. Now, water pollution as in the form of fuel and oil discharges. Then it can have in the form of domestic agriculture, food industries, and then it can be result from the agricultural products, pesticides, fertilizers, then heavy metals and industrial waste can cause water pollution. So these are the basic effects of these contaminants, different categories of contaminants. Then the flotation and low degradation due to these type of pollutants, then deoxygenation, the removal of dissolved oxygen from water can take place due to this type of waste. Then eutrophication, the lake eutrophication can take place due to this type of waste. Then, of course, the water can become very toxic and very harmful if we have these waste in the water. Now, let us briefly talk about the objectives of this session. The objectives of water treatment for domestic consumption. So basically, these are the objectives of this water treatment. To provide water free from these factors: visible suspended matter, color, taste and odor, objectionable dissolved matter, bacteria indicative of pollution, aggressive constituents. Now, why you don't like visible suspended matter? Because will you be willing to drink water with a lot of suspended matter? No, right? Nobody is willing to consume or use water with a lot of suspended matter. So that's the issue. Then color, odor, and taste. It should not have undesirable color, taste, and odor. Then it should not have this objectionable dissolved matter. We will be talking about dissolved matter later. Now, it could have certain chemicals dissolved in it, which could harm our health. So it should not possess, it should be free from objectionable dissolved matter. Then bacteria of harmful nature or indicative nature of harmful substance should not be there in the water. Then aggressive constituents, the things which react quick, fast. Let's say alkalinity, acidity. If you have too much acidity, it will corrode your equipments, your utensils. Now, let us briefly talk about the ways and means of measuring pollutants. Basically, we measure the quality of water using a set of parameters called water quality parameters. Now, these parameters are generally classified into three categories: physical and chemical parameters or physiochemical parameters, then radiological parameters, then biological parameters. Now this is a list of physiochemical parameters. You will be measuring fair amount of this at our labs. Then these are the physical parameters, temperature, things like that, alkalinity, hardness, and electrical conductivity will be considered as physical parameters. Then radiological parameters, of course, we don't measure that much of radiological parameters at this level, but if we are quite sure of a radioactive material contamination, under such circumstances, we can measure radiological parameters. Then, of course, biological parameters, we check into various fungi and protozoas and undesirable waterborne parameters. So, let us talk about the physical characteristics which are significant for proper water supply. Temperature. It is important for its effect on other properties such as speeding up chemical reactions, changing solubility of gases, amplifying tastes and odors. It's a catalyst. Temperature. High temperature means high energy levels in a substance. So if you have high energy level in a substance, it will speed up chemical reactions, changing solubility of gases, and amplifying tastes and odors, things like that. Then when it comes to taste and odor, due to dissolved organics in nature. So when organic matter dissolve in water, impurities often phenols and things like phenols difficult to measure. Now these things will create undesirable tastes and odors. Now nobody will like to consume water with undesirable tastes and odor. So that's why we have to be very careful about measuring taste and odor. Now when it comes to color, color has to be also desirable. Let's read. 1 second, please. Sorry. Now we were talking about the color. The true color is due to material in solution. The apparent color due to suspended matter. If a material has a true color, it is the color due to the presence of material. Now, if it has some other color, it is due to suspended matter dissolved in water. The natural yellow color in upland catchment water is due to organic acids and is harmless. Now, if you look at rivers coming from upper catchments in our country, it has this natural yellow color. They are due to organic acids mainly. They are fairly harmless. Now, this unit color is generally measured in a unit called Hazen. Right? Now, let us talk about the property turbidity. Now, turbidity is a fairly significant one, and we do a fair amount of work to reduce turbidity in water treatment. Now, colloidal solids give water a cloudy appearance, aesthetically unattractive and possibly harmful. Maybe due to clay and silt particles, sewage, or industrial waste, or microorganisms. Now, turbidity means unclear water. It is not transparent, you cannot see through it. And when the transparency goes down, the turbidity goes up. So it's a fairly important one, because if the water turbid, it could mean it is containing any of these substances. And if it has mud particles, the problem with mud particles is that it can hide harmful bacteria and viruses in these particles. So it is very important. In fact, in a treatment chain, there is a significant component dedicated to remove turbidity. Well, the other parameter is electrical conductivity, depends on quantity of dissolved salts and approximately proportional to TDS, total dissolved content. Now, especially this TDS refers to the salt content in the water. If the electrical conductivity is very high, it can have very high total dissolved solids. Now, if the dissolved content is very high, it could harm our crops, it could harm our soils, and ultimately it could harm ourselves. So therefore, measuring electrical conductivity is also fairly important. Now, when it comes to solids, it could be organic or inorganic matter in suspension or solution. So there are several types of solids. Total dissolved solids, normally denoted by TDS, are due to soluble material. Suspended solids, SS, are discrete particles which may be filtered out. Settlable solids are those which settle out in graduated cone after standing for 2 hours. Now, these are called Imhoff cones. You can see it in the lab. Now, let's go into chemical characteristics. pH, of course, it indicates us the alkalinity and the acidity level of water. Now, alkalinity is due to the presence of bicarbonates, carbonates, or hydroxide. It is useful as it provides buffering to resist changes in pH. Now, if you have high alkalinity, it could resist changes, right? Then acidity, especially if water becomes acidic, if you have too much carbon dioxide dissolved in it, when you dissolve carbon dioxide in water, it will create carbonic acid. So basically, these sort of ranges are present in water, in natural waters. Then there is an acidity called mineral acidity. This is usually caused by sulfuric, hydrochloric, and nitric acids. Would normally be due to industrial waste. Now, if you have industrial wastewater discharges into water, if the pH level is below 4.5, it's a clear indication of industrial contamination. Normally, it is measured in milligrams per liter of equivalent to calcium carbonate. Now, when it comes to hardness, now, how many of you are there from Rajarata and Hampantota and Ampara, Jaffna areas? How many are there? Nobody? Nobody is from Jaffna. Nobody is from Anuradhapura? I can see if you are there. Yes, thanks. Okay, right. Hardness, the property which prevents leather formation with soap. Arid produces scale in hot water systems due to metallic ions of calcium, magnesium, and ceruleum. So basically, this hardness you have experienced, it tastes bad, and you cannot, especially the people from wet zone, find it very difficult to drink, and it creates scales in your hot water pots. Then it also doesn't form the leather in with soap. So it creates cleaning difficulties. So this hardness of two nature, carbonate hardness and non-carbonate hardness, we might be dealing in extensively later. Carbonate hardness means the hardness by cations, anions, carbonates, and bicarbonates. Non-carbonate hardness means chloride, nitrate, and sulfate hardness. So the further these chemical characteristics are going to be there. Then this one is a very significant chemical parameter, dissolved oxygen, required for maintaining higher quality of biological life in water. Now, if the dissolved oxygen go below a certain level, the fishes and all the other living beings in that water will die. So therefore, it is fairly important to maintain very high dissolved oxygen. Further, the other thing is that in drinking water, if you have a high amount of oxygen dissolved, it will prevent other chemicals or other substances of occupying spaces in interstitial particles, right? Now you have water particles, molecules, and you have interstitial spaces among these molecules. Now, if you have high dissolved oxygen level, it will reduce other substance getting dissolved and getting into these interstitial spaces. Then the other thing, it will increase the taste of water, dissolved oxygen. Then nitrogen, it is present in 4 different types. You will you can read it from your notes, and It will come up later. Then chlorides give a brackish taste and may be indicator of sewage pollution due to chloride content of urine. Now, if you have high content of chloride, it means it has a definite sewage contamination. So detectable at about 250 milligrams a liter upwards. Now, let us briefly talk about the drinking water standards for Sri Lanka. Now, in the past, we had several drinking water standards or potable water standards. Now, this is the latest one, SLS 614 2013. This is the latest standard. The limits declared for each water quality parameter is the maximum permissible limit. And you can see now there is a set of parameters given in this table and set of parameters given in this table as well. They are biological requirements. Now, the minimum permissible limit is given. If our treated water comes beneath or below this required minimum permissible limit, we can say that it is fairly safe for us to consume that water. So by water treatment, what we generally try to achieve is these standards. Okay. Now, before moving into water treatment systems, we have to discuss few things about forecasting water demand. In order to design a water treatment facility, we should predict the future demand for water caused by population growth. There are two models to predict the future demand, namely linear model, exponential model. Now, when you are making a water treatment plant, you have to make a water treatment plant to cater future demand. So that you have to decide whether you are going to get 30-year predicted flow demand or 25-year predicted demand. But to predict, there are two types of models. One is linear model. You can see the linear growth with years. And this one is the exponential model. I have taken down this section, the design manual of the water board. And you can see, basically, we generally use this exponential model. Now, if you look at the exponential model here, Pn equals P into 1 plus R into N. P is the base population. Let's say we are talking about 2022. If the population is 100,000 in the command area, you can apply this equation and find the population in 30 years time. So this R is the growth rate. It was given as 2.3 and the manual that I was using was a pretty old one. In fact, these growth rates have come down significantly. I think it's close to one or something in Sri Lanka now. Then you can substitute number of years. So you can predict the population in 30 years or 25 years. For that population, you have to design the water treatment plant, your water treatment system. Then steps in determining the water demand. There are several steps in determining the water demand. Now, first step is to select a per capita water demand. 1 second, please. Sorry. Steps in determining the water demand. Now, the first step is to select the per capita water demand for domestic use. Now, if you go here, now this table here gives you per capita water demands, right? Now, for medium rural communities, normally it is taken as 120 liters per capita day. That means per person per day. Then large rural, let's say 1,500 to 5,000. It is around 140 liters per capita day. Then medium urban, 10 to 20,000. It's 185. Then large urban over 200,000 needed to be separately assessed. For that, there are several assessment methods. Normally, that has to be used. I think around in Colombo, it's around 250. Now, if you go to a city like New York, this might be around 500. I mean, with the scale of development, the per capita demand goes up. So it's a challenge, right? Right. Back. Now, next step is to determine the institutional demand. Now, within the command area, you can have various institutions such as these hospitals, hostels, boarding schools, restaurants, things like that. Now, for each and every institution, you have to calculate the water demand. For example, let's say hospital. Normally, it is calculated per bed. You can see this liters per capita per day per bed, right? Then hostels also per bed. Then boarding schools per resident. Then restaurant per seat. See how many seats of the restaurant the seat has, how many seats the restaurant has. Then for bus and railway stations per user, day schools per pupil, officers per person, factory per person, cinema per person. Now see, for cinema it is very low. I mean, we are not going to have bath in cinemas, so it is fairly low, right? So these are probability, these are calculated based on probability. So next one is to determine the industrial demand. Now, when it goes to industry, you have to determine based on industry, right? Then you have to estimate the total demand. You have to add the calculated one for domestic consumption. Then you have to add the calculation for industrial. Then you have to add the calculation for institutional. So you will get the total demand. Now, on top of this total demand, you have to estimate the non-revenue water. Non-revenue water. Now, this non-revenue water is an interesting thing. I will talk about it. Now, I'm quite sure you have experienced such things in our water system. You might have experienced water leakages in our systems. As such, these are all non-revenue water. What do you mean by non-revenue water? It does not generate any revenue to the institution or the government. These are just leakages. Now, for example, I know sometimes back at Peradeniya University, the water bill during the holiday months and working months are the same. So you cannot have a water bill during holiday months and working months the same. You cannot have. Why? Because during working months you must have higher water consumption. You must have lower water consumption during holiday months. This is due to non-revenue water, due to leakages in the system. Now, when the system or the pipe networks become older, this non-revenue water goes up. And this chart I have obtained from European Union. You can see the percentages of different countries in the European Union. You can see when the country become undeveloped, the percentage of non-revenue water goes up. You can clearly see that. Then I will move into water treatment plant. For that, this moment, I would like to take a 10 minutes break. I will try to share a video for you. Please watch during this 10 minutes time. 1 second, please.
You might have seen videos like this before, but here's the big secret. Anyone can make one of these videos in a few. Access to fresh water is
Okay, I'll share this small video. Please watch for a break.
Is one of the largest drivers of creating a modern society. But what allows everyone access to seemingly endless supplies of potable water? It depends on where you live, but chances are behind your tap, there's a municipal water treatment plant. There are two main types of water treatment plants: drinking water or wastewater plants. We'll be focusing in on drinking water plants here, but if you'd like to learn about how wastewater is treated, you can watch the video linked in the upper right here. The question still remains, how exactly does one treatment plant take dirty river water or well water and turn it into water that is safe to drink? It involves a lot of processing, using chemicals, filters, and removing all of the toxins and hazards from a given source. The entire process starts with something called coagulation and flocculation. All drinking water has to come from somewhere, usually being freshwater lakes, rivers, wells, or streams. In these water sources, there's going to be some amount of sediment as well as organic materials in the water. These particles of sand, bacteria, dirt, wood, etc., they all have to be removed before the water can be sent out to city residents. To do this, chemicals called coagulants are added to the water. These chemicals, such as aluminum sulfate or ferric chloride, work to help the particles in the water congeal together. Essentially, these chemicals have the opposite charges of suspended solids, like clays or silts. When combined, the charges of the particles are neutralized, allowing for them to stick together. Coagulants are often added to the water right at the inlet of a drinking water plant, where the water then goes into mixing basins called flocculation basins. In these basins, the solution of water and coagulant will slowly be mixed together to form what are called floc particles. After mixing for a set amount of time determined by water quality in the flocculation basins, the water is moved to sedimentation basins. It's in these holding tanks where the water sits for the floc particles to begin settling out at a faster and faster rate, which is the intended goal of this process. By simply adding and mixing these chemicals into the water and letting that water sit, a large portion of the sediment will settle out to the bottom as sludge, which can be taken away to a landfill or holding facility. The floc particles are ultimately removed from the bottom of basins, and the clean water, being the cleanest at the top due to the settling particles, flows over weirs to the next stage in the process. In some plants, engineers actually use dissolved air flotation tanks in place of sedimentation basins. In these cases, air is pumped into the bottom of the tanks, creating a cascade of tiny bubbles. As these bubbles float to the surface, they take floc particles with them, forming a film of floc on the surface of the tanks. Then, a sweeper arm pushes the floc into a collection basin where it's taken to a handling facility. In dissolved air flotation tanks, the clean water is taken from the bottom, where the least amount of floc is. When it comes to designing wastewater treatment plants, engineers will vary techniques based on the water source and how they want their final water to taste, feel, or otherwise be treated. The only regulation is the quality of water being pumped to the city, and in most cases, it doesn't matter how plants get the water to that point, which allows civil engineers a lot of creative freedom in the process. After the majority of solids are removed from the water during coagulation and flocculation, followed by sedimentation, the water flows over weirs to the next step, filtration. The water at this point will start looking clear, but there will still be bacteria and very small suspended solids in the mix. The filtration process will seek to remove the remainder of the suspended solids and bacteria to further bring the water up to snuff. Nearly every potable water treatment plant will use a sand filter for this process. Even in plants where engineers may not think it's needed, often sand filters will be added simply for extra measures to ensure clean water at the end. Sand filters are exactly what they sound like, a basin of fine to coarse sand that filters water. It would theoretically be possible to treat drinking water with only sand filters, but that would result in frequently clogged sand filters, resulting in lower efficiency and more cleaning time. These sand filters can be set up in essentially two different ways. Either the water flows from the bottom and exits the top, or the water flows from the top and exits the bottom. Each layout presents its own set of unique problems, but the most common technique is actually for the water to flow from the bottom to the top. Sand filters aren't highly technical. Water just passes through them and particles get caught as they run out of space to flow through. However, while not highly technical, sand filters are highly efficient. Water flowing out of sand filters will need to have a clarity of around less than 0.3 nephelometric turbidity units, or NTU. Try saying that 3 times fast. Or whatever local code is used for water clarity. This measurement is essentially just a way to determine the number of particles still remaining in the water, or turbidity. Many treatment plants will also pass water through activated carbon basins, which you can essentially think of as giant Brita filter tanks. Activated carbon particles have hundreds of tiny pores on them that help remove the tiniest of sediment and bacteria. This process isn't wholly necessary, but it helps improve taste and odor, often a desired trait for city residents. At this point, the water should be mostly crystal clear, but there still remains some residual bacteria. That leads us to the next step, disinfection. There are 3 main ways of disinfection in the water treatment process, which can be used individually or in combination with one another, depending upon design. First, chlorine or chloramine treatment, there's ozone treatment, and finally, ultraviolet radiation treatment. In the US, the main method of disinfection is by adding chloramines, or chlorine-based compounds. These compounds, such as chlorine dioxide or monochloramine, work to kill microorganisms. One downside to this process, though, is that these chemicals can react with other organic material in the water to create disinfection byproducts. These disinfection byproducts are harmful to human health and have to be prevented or mitigated. This extraneous reaction with other organic material is also why chlorine disinfection must come at the end of the treatment process. If added at the beginning, an abundance of disinfection byproducts would be created, causing a plethora of issues for the engineers and plant operators. Even with all of this, chlorine is used mainly because of how it kills pathogens. It not only kills any pathogens in the water at the plant, but residual chlorine levels also remain in the tap water, killing any contaminants that might get introduced after leaving the plant. Most cities or states will have maximum or minimum chlorine levels in the treated water in order to keep both the water treated and city residents safe. The other most common method of treatment is ultraviolet radiation. In this process, UV light is shined through the water, which scrambles any bacteria's DNA. This doesn't kill the bacteria, but it makes it impossible for them to reproduce, thus making them harmless. The main downside to this disinfection process is that it isn't residual like the chlorine, meaning that any bacteria introduced to the water after this process can't be treated. Finally, we're left with ozone treatment. This process involves adding ozone, O3, to the water. Called ozonation, the ozone kills the bacteria in the water as well as improving the taste and odor. In most cases, this treatment process also requires that a chemical be used to remove any ozone at the end, such as sodium bisulfate, as not to cause any harmful effects to the city's population or anyone who might drink the water. After the water is treated, in any one of these 3 disinfection processes, it's ready to be pumped into a city's pipe network for delivery to your tap. The water flowing out of a plant is tested for various levels of chemicals, particles, and other qualities all outlined in a plant's permit. This permit, set by the governing agency, regulates water quality and holds the treatment plant accountable in the treatment process. At this point, all the water is fit for human consumption per the permit, and the treatment plant is tasked with keeping it flowing through the pipes in your city. Constant pressures of 40 psi must be kept at the outlets of the water in the system so that in areas of high elevation in the pipe network, the water retains residual pressure. 1 foot in water elevation is directly correlated to an increase or decrease of 0.433 psi. So as water is pumped throughout the city, its pressure at any given point of differing elevation fluctuates. Positive pressure always has to be achieved as to not let any external water in the ground flow through pipe cracks or joints. This would contaminate the entire system and is one reason why you might experience a boil water notice. Essentially, that means engineers have reason to believe that somewhere in that city's pipe network dropped below the required PSI and water or contaminants might have infiltrated the system. Massive pumps at the treatment plant supply pressure to the system through constant operation. Some of this pressure can be stored as elevation in water towers, which can give pumps a backup in emergencies or fire flows. In a lot of cases, water towers allow the pumps at the treatment plant to run at a constant rate, which increases efficiency and removes downtime problems. This combination of pumps and water towers allows your tap to remain flowing and otherwise allows you to live in the comfort of your own home. Civil engineers and treatment plant operators work around the clock to provide clean water through water treatment plants. At this point, we've taken a look at the most common potable water treatment techniques, but there are tens to hundreds of other deviations we haven't discussed. This draws back to one of the coolest things about water treatment plant design. You're able to use any number of creative solutions to clean the water, and as long as it comes out clean, you've done your job well. Don't forget about the thankless job of being a water treatment plant operator, though. These men and women work around the clock to keep treatment plants running 24/7 so you can always have fresh water. A lot of time, money, and effort goes into making sure that you can have that nice glass of water on demand.
Okay. Hope you have enjoyed that video. I'm quite sure it enlightened you a few things about water treatment. So it has briefly discussed about water treatment, but there are so many steps involved in it, a lot of theories involved in it. Even this course covers the basics of it, not in-depth analysis. If you do a master's on this, you might come across in-depth analysis of water treatment. Okay, one minute, please. Later, I will download this video and upload it to LMS. Please use LMS. Okay, I'll start sharing. Now, this was what it was talking about. It is a water treatment plant. Now, this treatment plant gets the water from a natural source. It could either be a well or a stream or a fresh water, deep water tube well. First, generally we do a screening to prevent large debris or large particles entering into the system. Then it will generally lift up to create the required head in the flow. Now, in this treatment unit, the first step is called coagulation, then the sedimentation, then the filtration will take place. Now, in combination of all these three steps, coagulation, sedimentation, filtration, we call it clarification. You can clearly see it here. So in combination of coagulation, sedimentation, and filtration, we call it clarification, this part, right? So now, during the first step of coagulation, we add coagulants and we give a thorough mix here, and the mixed water will be sent into a flocculation tank where it creates flocks, and the flocks will be removed through sedimentation, large flocks. Then if there are any other flocks or substances that will be filtered out using rapid or dual media filter. Then that filter, then that filtered water will be generally disinfected. Now, I think you came across several disinfection methods in that video. Now, after disinfection, it will be pumped into the distribution network or a storage tank. Then thereafter, it's about distributing water, not about treating water. Now, if you look at the treatment mechanisms, it comprises of this list generally: screening, aeration, coagulation, mixing and flocculation, sedimentation, filtration, disinfection, storage, and distribution. Now, these steps are the major steps in a treatment mechanism. Now, first we'll talk about this, this section, screening, right? Now, under screening, we will be, now, there are two different forms of screening, pore screening and fine screening. You can see in these pictures, there are different forms of screeners available: drum screeners, mechanically removed screeners, manually removed screeners, bar screeners, various types of screeners are there. For river and lake intakes, some form of protective boom or core screen about 75 mm opening should be used to prevent large floating objects entering the intake. So you can see large debris like, coconut husk, then sticks, things like that. So this space between these two bars might be around 75 mm. The velocity of water through the screen opening should not exceed 0.5 meters per second. I mean, these are design parameters. When the water flows through the screen, it should maintain a velocity of 0.5 meters per second. Now, this is a general arrangement, and this picture here shows the schematic diagram of a cross-section of a core screen. Let's say the cross-section of the water depth is AC and it is tilted at angle theta, and let's say the cross-section, the area of the screen is AS. Now, these are the design criteria. I mean, I'm quite sure you are familiar with design criteria. I believe most of you have passed structural analysis, and hopefully most of you have done structural designs. So design criteria are the governing laws for the design, right? Now, the approach velocity VA has to be, I mean, as it clearly said, not exceed 0.5 meters per second. So that has to be achieved in the hydraulic design of the system. Then bar spacing has to be, now the spacing between these two bars has to be 50 to 100 millimeters. You can select any value. Then bar thickness, let's say the thickness of a bar should be around 15 millimeters. The maximum allowable head loss. Now, when water goes through a hydraulic structure like this, generally the energy level of the flow will reduce. Now, that reduction should not exceed 150 millimeters, around about 6 inches. Then the depth of the bar D has to be 0.5 to 1 meter. It should not be that long, that deep. The angle of slope is theta from vertical. Let's assume the angle of slope theta from vertical. Now, this is the general design calculation for bars. I am not supposed to do a design lesson in this class, but for your information, I thought of putting this up, and I'm sure under 7242, you will get more design data about bar screens. Then let the canal cross section, the canal cross section here be Q divided by VA. I mean, the flow rate divided by the velocity will give the canal cross section. Then the screen cross section is AC sec theta. I mean, then it comes from trigonometry. You can see if this is AC. If you want to get this AS, it is AC sec theta. If you want to get AC from AS, it is AS cos theta, right? AS cos theta. Now, in this way, it is AC sec theta, right? Then white space ratio. Now, there is a ratio called white space ratio, that VSR is equal to space between two bars divided by space plus thickness. Now, if you calculate the cross-sectional area of the bars and the spaces, and also if you calculate the cross-sectional area of the bars, generally it will come up to this equation: space divided by space plus thickness. That is space over overall cross-section area. Now, net area of the flow. Net area of the flow means when flow goes through this bar screen, it will not go through the area of the bars. Am I right? So basically, the flow will flow through the void spaces between these bars, right? It will flow through the void spaces between these bars. So this void spaces has the area of the void spaces is generally calculated as A net. A net is calculated by multiplying the total screen cross section by the VSR. The velocity through the screen is VB, generally given as VB. It is obtained by flow divided by A net, effective this net flow area. Then, the approach velocity is given as VA. I mean, it should not exceed 0.5. That is what it says. That is the velocity in the canal. So basic head loss is calculated using this equation. This is a general equation that we study under hydraulic structures or under hydraulics. So VB squared minus VA squared over 2G into 1 upon 0.7. So this is about that. So you can calculate the head loss through the screen with this equation. If that is below 150 millimeters, then your design is acceptable. Assume a value for the depth of D and calculate all the dimensions of the screen. Generally, we assume a depth of the screen, then you can calculate the dimensions for the entire screen. Then we will talk about fine screens. I'll give you 1 minute to read this. Could you please read this? Now these fine screens Fine screens are usually 5 to 20 millimeter opening. Duplicated screens being provided to allow the removal of one screen for cleaning manually. Usually you have two screens. One is there uh, to stand secondary or as a alternative while cleaning other one. Alternatively, provision may be made for cleaning by raking or water jetting. Now, I am quite sure you know what is a rake is. You have put the rake or either water jetting is allowed to clean the debris. Maximum velocity through the screen medium should not exceed 1 meters per second. Mechanical screens may be necessary or larger schemes operated continuously or intermittently as controlled by the loss of head across the unit. For a belt type screen, 15 millimeters per second would be typical belt speed. There is a belt. You can see this on the internet. Now this belt will go up and down and it will, the screen is a moving belt. Water is going across that. So whatever trapped on the screen will move, mechanically remove. Now we are coming into the aerators. Now aeration is a significant part in Sri Lankan water treatment systems. Now before getting into this, what do you call this step? Clarification. Generally, we have aerator before clarification somewhere here. Now, unfortunately, in this system, it does not show aeration. For certain countries, this aeration is not that required. But in Sri Lankan context, especially in wet zone, aeration is required. Basically, the aeration of water, which is obtained from sources such as lakes, rivers, and deep wells, needs to be aerated to achieve these things. First one, let's read. To reduce anaerobic water. Now, anaerobic water means the water contains less amount of oxygen and also contains, foul gases like carbon dioxide, ammonia, and hydrogen sulfide. So when you do aeration, most of these undesirable gases will go out from the water and desirable gases such as oxygen will get dissolved in water. Then next thing is to increase pH about 0.5 so that the iron and manganese can be removed and reduce corrosivity in water. Now, if we increase the pH above 6.5, the iron and manganese can be removed and reduce corrosivity in water. So basically, you can reduce anions and manganese anions. To increase dissolved oxygen level, which is essential for drinking water, for it to taste and smell good. Now, I told you before that we need to increase the dissolved oxygen level to a desirable level so that it increases the taste and the smell of water. This is caused by occupying spaces in water, preventing other minerals occupying it. I told you about this. I told you about the interstitial spaces. If the interstitial spaces are occupied by oxygen, it will not be occupied by other minerals, right? I will move into the type of aerators. Now, basically, there are three types of aerators, namely spray aerators, multiple tray aerators, and cascade aerators. Now, when it comes to cascade aerators, multiple platform aerators and step aerators are there. Now, you can see this is a multiple platform aerator and this is a step aerator. You can see water flows in steps. sorry. Now, now in the step aerators, you can see that water flow in steps. Then in multiple platform aerators, there are multiple platforms available and water will be flowing from the top and it will be aerated. Now these are spray aerators and multiple tray aerators. In Sri Lanka, we have these two types mostly available. I'm quite sure you have seen such structure operating in adjacent to water treatment plants. And we'll further move. Now let us talk about the first step of coagulation. Now the objective of coagulation is to turn the small particles of color, turbidity and bacteria into large flocks, either as precipitates or suspended particles. Now basic idea is to make small particles into large particles so that they can be removed by gravity and filtration. Coagulation is defined as a method to alter the colloid so that they will be able to approach and adhere to each other to form large flock particles. Now, by doing coagulation, we support these particles to glue together. The group of chemicals called coagulants are added to induce particle agglomeration to create above described coagulation. Now, what we add a group of chemicals to accelerate this agglomeration. We call this process agglomeration, okay, to create above described coagulation. Right. Move further. Now, these things we have discussed before, but I think this picture will explain you better. There are 4 types of solids from soil dissolved in water. Now you can see floating solids are there, which floats on water. You can easily remove them with filters or scammers. Then scummers. Then there is something called suspended solids here, which are suspended between water particles. And there are solids which are called settled solids. These can be settled using grit chambers or gravity. And there are things called dissolved solids. Now in this water, even though it is very clear, there are solids dissolved, basically minerals. Now these are dissolved solids. They have to be removed chemically. Now what we are going to mainly focus about what is here, which is called suspended solid. That is what we target with coagulation. Now, if you move further, now we'll talk about the negativity of soil particles. Now, if you look at the creation of, or the ingenuity of the natural ingenuity of the soil particles, now basically it contains aluminum or magnesium with silicon. And the orientation will result in the soil structures like pellets or solids or things like that. Now, basically they are in the form of silicon tetrahedrons or metallic octahedrons. And you can see it here. Now, according to this, you can see the positive cations are inside, the negative anions are outside. Now, when the crystals are created from such structures, the negative things will be on the surface and the positive cations are inside. So generally, the clay particles are of negative nature, okay, are of negative nature, right? Even octahedrons produce similar things, right? So if you read this, the negative charge helps colloids to be suspended among water molecules. If the negative charge are destabilized, particles can flocculate and settle easily. Such neutralization can be achieved by adding cations to the solution. Now, what you have here is a negative particle. If you have another negative particle here, they will repulse each other. And due to this repulsion, they will suspend in water. And the suspension forces are so great that the particle gravity, these small particles, gravity is not enough to settle it down. So if you can neutralize these negative charges, you can simply allow it to glue together and come down. Now, basically, we use cations as coagulants to neutralize this surface charge. Now, let's briefly talk about the effect of valency and cation on negative charge on soil. Now, you can see, I will allow you to read it for 1 minute. Please read. You can read it. Now you can see if a crystal has negative charge here, the surrounding positive charges will be there around that, but still the negative charge or the charge field will be there. There will be a slipping plane which is not that closely packed onto, we call it this Burns layer, and beyond this layer, the potential or the electric charge available to attract other positive charges is called zeta potential. So what we do is addition of cations to neutralize zeta potential, right? Now these graphs are not that clear, but I have taken from the standard textbook that I am using to teach you. It is there in your the blocks as well. Now, if you look at the electric potential with the distance from the surface of particle, now the same graph, this one, if you move it away from the surface of the particle, and if you plot the electrical potential or the zeta potential, so you will have a diagram like this, right? Now, when you put sodium chloride, negative surface charges of clay minerals, you can see if you put high salt into it, the zeta potential will go down quickly. At low salt, no salt, it will be there. Now what happens is when you mix sodium chloride, sodium cation will try to neutralize this charge quickly, this zeta potential charge. So that is why at high salt, the zeta potential has moved very low at this point. Then distance from surface or particle. Now when you move away from the particle, then valency. Let's say, what is valency? What is the valency of sodium? Can somebody answer? What is the valency of sodium? I am quite sure you have studied it in A-level chemistry. What is valency of sodium?
3.
Sorry.
3.
Sodium valency?
3. 3, sir.
Sodium?
1.
1. Sodium has 1 plus charge. So the valency is 1. What is the valency of magnesium? Can somebody answer? I mean, you have to integrate. I mean, I have been
So-
lecturing like a
9. Magnesium 9.
magnesium 9.
No, sir. 2.
2.
It is 2, right? Now, the charge the magnesium creates when it becomes a cation plus 2, right? So this valency you have forgotten. This is why you have failed A levels. Most of you. Right? The valency is what you call the charge, right? Either it could be negative. So what is the valency of chloride? Tell me. What is the valency of chloride?
1.
1. Very good. Right? So now here they are putting, cations. So you can see the variation of zeta potential with the valency, right? You can see it from here, right? You can see electric potential moves down with valency, and here you can see valency plus 3 reduce electrical potential quickly with the distance. That means what we are referring is this. If you put cations with valency 3 plus, so what you get is the zeta potential will move quickly. It will reduce quickly, right? So that is what it shows here. Okay. Now, if you put sodium, it will move like this. If you put magnesium, it will move like this. Likewise. So we have to select a coagulant with that in mind. Okay. So I'll give you 1 minute to read this slide. Please read it. Okay, let's read it, right? The substance that we mix to neutralize negative charge and create clogs are called coagulants. There are 3 properties of a coagulant. I mean, basically a coagulant should satisfy these 3 properties. It should be a trivalent cation. It should be non-toxic, obvious for safe drinking water production. It should be trivalent cation. You saw during this graph, it should, if the valency is high, it is good. So the highest the valency is 3, so it should be trivalent cation. Non-toxic, it should not be a toxic because we are making drinking water. Then it should be insoluble in the neutral pH range. Now, when the pH becomes neutral, it should be insoluble. Why? The coagulant that is added must precipitate out of solution so that high concentrations of the ions are not left in the water. Now, when you add coagulant, it should settle down under neutral pH. Otherwise, if it remains suspended, it will become a hazard for consumers, right? The two most commonly used coagulants are aluminum and ferric iron, right? Al3 plus or Fe3 plus. Both meet the above three requirements and their reactions are outlined here. When alum is added to a water containing alkalinity, the following reaction occurs. So if you add alum to water containing alkalinity, here it represents carbonic acid. So it creates aluminum hydroxide, carbon dioxide, then sulfate. Above reaction occurs when sufficient bicarbonate are present with high alkalinity. This reaction tends to reduce pH of water, which can adversely affect the coagulation process. Now you can see, if you look at this reaction, closely, you can see that for this reaction to take place, to create aluminum hydroxide, it needs to have carbonic acid. So basically it has to have some high alkalinity. And also you can see this reaction produce an acidic substance, sulfate, right? Now, you know, in water, there are high amount of protons or H plus. So if the sulfate mixed with water, it can create acid. So can adversely affect the coagulant process. So this acid could reduce pH, reducing alkalinity, so that the process could inhibit, right? So let's talk about effect if alkalinity on coagulation. When sufficient alkalinity is not present, the following reaction will take place, causing pH to reduce greatly. Now, if you don't have enough alkalinity in this side of the reaction, what happens is that it will create the reverse reaction like this. This aluminum hydroxide will react with sulfate again and will produce aluminum sulfate H2O. Okay, so you have to be very careful. It is found that the optimum pH is approximately 5.5 to 6.5. To maintain this range, the addition of calcium hydroxide, you know, this calcium hydroxide is added to maintain the alkalinity this side, so that the forward reaction will take place. So generally we put calcium and the alum and lime. This is called lime and this is called alum together. Why we put lime? To maintain enough alkalinity. Now let's talk about flocculation a little bit. See how many slides are there. Get test, jar test, stability of water. Yeah. So the time is not enough for today, right? Jar test, stability. So we will stop here, right? We will talk about the coagulation and flocculation and various things in the next class. Okay, thank you very much. I don't think I will be able to share this on I will able to share the slides on LMS, but the video I will share it on my YouTube channel called GunnyTube. In fact, I have created this to support students. Right? I'm just typing it to you. You can see it on the chat. And thank you very much. Do you have any questions? Please ask. No questions. Okay. Right. 1 second. I want to get your attendance. You don't, since you don't like to talk.
Sir, how many sessions will be covered to for Cat 1?
Cat 1 I'll cover. I'm doing the session 4, right? Then I'll be covering block 1, like session 1, session 2, and session 3. For Cat 1, I will use all these 4 sessions. Cat session 1, session 2, session 3, and this session 4. This is in fact a very long session, and it contains all the things relevant to water treatment. So to cover it up, at least I will use another 2 days course. Okay. Is it clear? Do you have any questions? Once.
Sir, when we can receive the study material, sir?
Sorry, I was in a call with Kamal sir. Somebody asked a question. Can you repeat the question, please? Hello? Somebody asked a question.
Sir, when we can receive the study material, sir? Because it is very important. Our
You didn't receive study material?
yes, sir.
You better check with the dispatch.
Sir?
Did you check with the dispatch?
Okay, sir. The soft copy also is
From where did you register?
medical, sir.
So don't you have a dispatch at the Baticular Center?
Yes, sir.
So why didn't you check it from the center? Now this study material distribution, printing, and everything is not a responsibility of lecturers.
Yeah,
we have given these things long ago to these people to print and deliver it to students. So could you please check it from the center?
Okay.
So you must know, you better before when you are registering, you must always check the materials at the center. Are there anyone else who does not have the material? Hello? Are there anyone else? Please raise your hand. I just want to know how many of you do not have study materials. Nearly half of the class does not have study materials. What's wrong? Did you ask it or didn't they have the study materials? What was the problem? Hello?
Excuse me, sir.
Yes, yes, tell me.
Sir, we request from the dispatch. This time they told they will issuing the material through the courier, but still we didn't receive the material, sir, for every subject.
You better inquire it again. I mean, do you have any contact with your student representatives?
We have told them, but still didn't get any response, sir.
To which center are you attached to?
So I'm from KRC, Candidate Regional Center.
So they have to distribute these things now. I mean, this is not our job. I mean, it's their job. I mean, I don't understand these people. Anyway, we will try to. Anyway, you follow my classes, okay?
Okay, sure, sir.
And later I will try to find a solution for this to this. And if this goes like this, I will talk to Vice Chancellor as well. I mean, I'm thinking of, because last time also they made a mess out of this study materials, and this time also, if they make a mess like this, it's going to.
For every subject, sir, this problem is there.
What are the subjects?
For every subject. This time we are taking level 5 subjects. For every subject, we didn't get any material still.
Okay. So no option but to write a. I mean, it's not our job. I mean, honestly, it's not our job. We have worked very hard to write the lessons for you, and we have sent them many years back. So it's their duty to print and distribute. So I don't know. Maybe I'll try to give you one session. So we will discuss this matter in the next day school as well. I'll be sharing these presentations. Please follow them. I will be sharing the videos. Okay.
Thank you, sir.
Okay. Right. Okay. Other than that, are there any other questions? No. Okay, then thank you very much. I'll stop the recording and I will upload the video. Okay, thank you very much.
Thank you, sir.